So good morning everyone, I am Masna Rajitha. Today I am presenting our project towards LLM-Assisted vulnerability detection and the repair. So the main aim of our project is to detect the security vulnerabilities in the source code using any large language model and automatically generate the secure repaired code for us. So our project is implemented using the Python Flask, HTML, CSS, JavaScript and the any large language model. So here we took as an example as Gemini API. So the second slide is core methodology. So this slide explains the overall methodology followed in our project. So the first step is source code input, where the user enters the C or Python code through our web application. So next, the code is sent to the large language model, which understands the code and analyzes it for security vulnerabilities. So after identifying the vulnerabilities, the large language model generates a secure repaired code of the repaired version of the code. So finally, the corrected code and the vulnerability explanations are displayed to the user through our Flask web application. So this methodology automates the vulnerability detection and significantly reduces the manual effort. So coming to the next slide. So in the first phase, we studied various research papers related to source code vulnerability detection. So we analyzed traditional root-based approaches and modern AI-based techniques. So we also studied how large language models can understand the programming languages and generate a secure code. So the literature survey helps us identify the limitations of existing approaches and guided the design of our project. So coming to the next slide. So in this ways, we clearly define the problem statement. So software developers often miss vulnerabilities during the coding. So manual code review is time consuming and it is error prone. So therefore, our objective is to develop an AI assistant system. Going to the next slide, it is system architecture. So this slide explains the architecture of our project. So the user enters the source code into the web application. So the Flask backend receives a request from the user. So it validates the input and sends the source code to the Gemini or any other large language model. So Gemini analyzes the code, detects the vulnerabilities, explains each issue and generates the repaired code. So finally, the analysis and corrected code are displayed on the web page. So moving on to the next slide, this is our final architecture diagram. So this slide shows a complete workflow of our project. So the process starts with the user submitting the source code. So the Flask server communicates with Gemini or any other language model which we are using here. So it performs a vulnerability analysis and secure code generation. So the final repaired code and detailed explanation are returned to the user. So this architecture provides a fast and automated security analysis. So moving on to the next slide. So the original research paper mainly discusses the only theoretical vulnerability detection. Our project improves it by developing a complete web application. So we integrated Flask with Gemini API for real-time analysis, or we can integrate the Flask with any other large language model for our project. So we also implemented the automatic phasing, secure validation, live vulnerability detection, source code generation, and proper error handling. So this enhancement make the project process practical and user friendly. So the next slide says that the original research paper mainly discusses the theoretical vulnerability detection only. So our project improves it by developing the complete web application. So we integrated the Flask with Gemini for real-time analysis. So here we can integrate this Flask with any other large language model. So we also implemented the automatic phrasing, secure validation, live vulnerability detection, secure code generation, and proper error handling. So this enhancement make the project practical and user-friendly. So next slide. This slide shows the performance of our project. Our AI assistant system achieved a much higher vulnerability detection rate compared to traditional approaches. So it identifies more vulnerabilities and generates a secure repaired code automatically. So this demonstrates that large language models can improve the software security. So the last slide. So in the future, our project can be extended to support more programming languages such as Java, C++, and JavaScript. So we can integrate the additional security testing tools. The system can also be connected directly to GitHub and CI or CD pipelines to perform the automatic vulnerability detection during the software development. So this will help the developers to build secure applications more efficiently. So now I will explain the implementation of the project in VS Code. So first we have to create a project folder. So this is our project folder named 5G vulnerability detection. So it contains all the files required for our application, including the front-end, back-end datasets, reports, and configuration files. So next is PyCatch. So this folder is automatically created by Python. It stores compiled Python files with a .pyc extension to improve the program execution speed. So we do not modify these files manually. So next, it is database. So this folder stores the application data. In our project, the generated vulnerability reports are saved in reports.json, which helps maintain previous analysis results. So next, datasets. So this folder contains a vulnerability rules.json. It stores the predefined vulnerability information used by the application during the security analysis. So next we move to the reports. So this folder shows the it stores the generated reports after vulnerability analysis. Each analysis results can be saved here for further references. So next we move on to static folder. So the static folder contains the front-end resources such as JavaScript and CSS files used by the web application. So next it is script.js. So this JavaScript file handles the interaction between the user interface and the Flask backend. So when the analysis button is clicked, it sends the source code to the backend and displays the returned vulnerability report and repaired code. So next it is style.css. So this file is responsible for the design of the web page. It controls the colors, fonts, spacing, layout, fonts, and makes the user interface attractive and responsive. So next is templates. So the templates folder stores the HTML pages used by Flask. So next is index.html. So this is the main web page of our project. So it contains the project title, source code, input area, analysis button, and output section where the vulnerability report and repaired code are displayed. So next is env. So it is a file which stores the sensitive environment variables such as API keys. Keeping them outside the source code improves the security. So next is app.py. So this is the main backend file of our project. It creates the Flash server, receives the source. So next is app.py. So this is the main backend file of our project. So it creates the Flash server, receives the source code from the web page, communicates with the large language model, and returns a vulnerability analysis to the front end. So next is config.py. So this file stores a Gemini API key or any other large language model separately from the main code. The backend imports this key whenever it needs to connect with the API. Next is detection.py. So this module is responsible for the vulnerability detection. It analyzes the submitted source code and identifies the possible security issues before the repair process begins. So next comes Gemini test.py. So this file is used to test the connection with Google Gemini. It verifies that it is working correctly and returning the responses. So next is repair.py. So this module generates the secure repair code based on the vulnerabilities detected. It generated an improved version of the code using the Gemini model. So the last one is report.py. So this module prepares the final vulnerability report. So this is our web application for LLM-Assisted vulnerability detection and repair. So the user can paste C or Python source code into the text area and click on the analysis code. So here I have entered a C program that uses the gets function. Since gets does not check the input size, it can cause a buffer overflow vulnerability. So the complete repaired code. So in conclusion, our project uses the large language model to automatically detect the vulnerabilities and generate the secure repaired code. So this helps the developers identify the security issues quickly and improve the software security with less manual effort. So thank you.